Hello and welcome to our instructional video titled A Cost-Effective and Informative Method of GPS Tracking Wildlife. This video is linked to a paper available in Wildlife Research. The funding bodies for this research were the Centre for Integrative Ecology at Deakin University and the Holsworth Wildlife Research Endowment. This video is divided into 5 steps, with the item for each step listed at the beginning, and then a demonstration video on how to construct that step. Step 1 is removing the commercially available device from its casing. We start by making sure the device turns on, which is the blue light. Once the blue light is flashing, it means the device is working, and we can turn it off again. This is important as the following steps void all warranties for the device. You can see the USB plug and the hook for the rope tie or hand strap. We want to cut through the casing over the hook tie. When cutting through the casing, be sure to do so as close to the edge as possible so that you do not hit the battery inside. Saw down through the casing until you can get a blunt instrument underneath the backing plate. Once you can, slide the blunt instrument along the backing plate to start to raise it from the rest of the casing. Use your fingers to remove the rest of the backing plate so that you do not damage the battery beneath. Once the backing plate is removed, we can now remove the rest of the casing from around the GPS device. Be careful at this point, as if you are too rough with the device, you will break one of the 4 pins which connect the USB plug to the chipboard. Gently break away the sides of the casing using some pliers and slowly slide the device out of the casing by the USB plug. It is a good idea at this point to make sure the device still turns on, off, and can be recognized by your computer. If it cannot, you have most likely broken one of the 4 pins which connect the USB plug to the chipboard. Step 2 is changing the battery. Our first step in changing the battery is to remove the original battery. We do so by snipping the wires of the original battery as close as we can to the chipboard. Remember exactly where the red wire was connected and the black wire was connected, as this will be important when connecting the new battery. Here we have a 3.7 volt rechargeable lithium-ion battery with tabs, but it has a higher milliamp hour rating. To begin, strip the plastic from the ends of the tabbed wires so that we can solder onto them. The replacement battery must be 3.7 volt rechargeable lithium-ion battery. By 3.7 volt, we do not mean the charge within the battery must be exactly 3.7 volts at all times. The actual charge will range from 2.75 volt to 4.2 volt. Once we've checked the charge, we can now solder onto the ends of each wire, which will prepare them to be soldered to the chipboard. We solder the red wire, which was originally connected to the red wire point first. Be careful when doing so not to solder onto the connection of the black wire. I start with the red wire as it is closer to the middle of the chipboard, and I find it easier to do first, leaving plenty of room for soldering to the black wire. Once the black wire is also soldered onto the device, we can check that the device still works. Here, the red light has come on automatically. If the light does not come on automatically and will not turn on by the button on the top, this means the device must be reconnected to the computer to reboot. Simply plug it in via the USB cord, load up the @trip software, and connect your computer to the device. The device should be rebooted and ready to use. Step 3 is covering the device in a thin silicone coating. Before we begin coating, I use a neoprene ring, which I glue onto the chipboard, to protect the button from being covered in silicone. It also protects the button on the finished device from accidentally being pressed. I simply apply glue to the neoprene ring and firmly press it onto the device. I then wait a few minutes for it to dry. Once the glue has dried, I take some blue tack to cover the button so that it does not get covered in silicone and will continue to work afterwards. I also cover up the USB plug for the same reasons, as we need both of these areas once the device is encased. The blue tack must be firmly pressed down so that the silicone does not get in. If the silicone gets on the USB plug, you can use sandpaper to clean them off, but you cannot clean off the button, so only scheduled starts will then be possible. Once the device is covered in blue tack, we can then spray it with silicone coating. Silicone coating stops dust, dirt or moisture from getting on the chipboard and causing rust or corrosion. Make sure to wear the advised personal protective equipment when using the silicone coating and move it to an area where it is safe to use it. We're using a fume hood. Spray an even coat of silicone over the chipboard and the battery pack. You can tell they are covered when they have a shiny yet wet appearance. Once they are coated, hang them out to dry for at least 24 hours. Step 4 is encasing the device. The first step is to remove the blue tack. Hopefully when you remove the blue tack, you will notice that the rest of the device is shiny, but the areas that you had covered do not have the same shiny coating. If they do have the shiny coating, it means that they are covered in silicone and you will have to try to clean them. Once the device is ready to be encased, we can do so with several materials. Here I am going to use an epoxy putty. Epoxy putty is available from most hardware stores. It comes as two parts which are then moulded together. In this instance, I'm going to make the epoxy putty black, as most commercially available devices for GPS tracking wildlife are black. You simply knead the putty together with the black dye until it becomes soft and malleable, a lot like clay. Once the epoxy putty is in this consistency, we slowly work it around the device to give it a thin but solid coating. I start at the connection plugs to make sure they do not accidentally get covered by the epoxy putty while I am kneading it around the device. Here I am complete. You can see that the lights are still uncovered, as is the button and the GPS receiver plate. The 4 plugs for the USB are still available, and I've added a slight curve to the device to better fit onto a collar. The next step is the optional step of connecting a VHF transmitter. I tape the VHF transmitter onto the battery pack to hold it in place while I encase it in epoxy putty. I then make up my epoxy putty like previously and work this over the device, leaving the frequency of the VHF transmitter available. I add a slight curve to this device and 2 spurs underneath to stop them from sliding out of the heat shrink, and also add a ridge to the GPS device for the same purpose. So here you can see I've got the slight curve, the ridges on both the devices, and when we put them down you'll see that they do make a ring ready for the collar. Step 5 is securing the GPS to the collar. Here I'll be using a leather collar commercially available for a dog or puppy. I start by sliding the heat shrink over the collar and over the GPS and wires. I then use a second piece to cover over the GPS itself. I use a heat gun over the heat shrink to melt the heat shrink and shrink it onto the device. I use a third piece on the battery pack to shrink that also onto the collar. Once this is complete, we now have a finished collar. You can see that the frequency of the VHF transmitter is still readable, the VHF antenna is still available, the GPS receiver plate is only covered by heat shrink, the lights are covered so they will not annoy a nocturnal mammal, the USB pins are still available, and the button is still pressable through the heat shrink using a blunt instrument such as the pliers. This is our complete collar. We'd like to thank you for watching our instructional video on how to build a GPS collar